that you have just heard. It's going to be very difficult to add anything new, but I have lots of slides, and I'm going to tell you specifically what Sony is now introducing in the area of IP for professional applications. We've been working on this for now almost 10 years. We saw the transition from SDI almost mandatory, and we had a lot of problems to solve. One of the issues that we recognized a number of years ago is that currently the industry is basically facing a double investment in infrastructure. We've been doing IP for quite some time in all of the workflows that we have in production and post-production. And that area basically doesn't need the low latencies and synchronization that we have in live productions. We have been using cost-down infrastructure using commercial off-the-shelf switches for quite some time. Therefore, the file-based environment is already very, very much aware of the benefit of going to IP because they've been doing it for a long time. While in the case of the live programming and live environment, we haven't had that experience. We need SDI base, we need real-time monitoring. It's always a constant bit rate. We cannot rely on best effort. Every time you punch a camera into a switcher, that signal has to appear instantly. Therefore, that model of best effort operations is not applicable, or was not applicable in the world of live production. We were accustomed to the dedicated routing environment where we have a specific routing from cameras to other points. Therefore, we had to implement a double investment in broadcasting and production and post-production environment. But the industry has to move on, and the only way to reconcile this double investment and to reduce economic costs is to adapt IP to a live production environment. And this is now happening right now, how we utilize IP technology to mimic perfectly what we have enjoyed in the world of SDI environment. Sony is very aggressive in implementation of products. We introduced a number of commercial products at NAB this year. There will be others at the end of this year. And we are following standards that seem to work. We're trying to promote changes, and we are introducing proposals that I'll discuss later to make existing standards work better. And one thing that is for certain, we cannot remove anything of the benefits that we have enjoyed in the existing SDI world. If we move to IP for live production, taking anything away from your operations, it will be a failure. Failure as a vendor and failure as an industry. Therefore, this is why the technical challenges are very, very important, and we have to confront them directly. We plan to introduce all of these IP interfaces, essentially not only for the broadcast station, but also for remote productions. Cross-connection between regional broadcasting stations and the main broadcast station, stadiums, arenas, remote productions in trucks, everywhere where your network reaches. This is where we plan to do. The benefit you have heard from the other speakers. I'm not going to go through them, but essentially we would like very much to use commercial off-the-shelf equipment. We don't want specialized switches. We don't want timestamp or time-aware switches that are only supplied by a few vendors. If we want to rely on the economies of scale of the IT industry, it has to be really, really very affordable IP fabric switching. All right, you can read the rest of the other benefits. We began this process of transitioning to IP a number of years ago. We introduced a point-to-point device that allows us to carry 4 HD signals over Ethernet cabling. And it was okay. We sold quite a good number of those units, but it was point-to-point. And it was very specific applications, concert halls, just to reduce wiring in specific areas of the broadcast center. But the ultimate goal was to go multi-point to multi-point. And we have developed a specific LSI that I'll discuss later that we are now introducing in all of our products. Production switchers, 4K cameras, HD cameras, monitors. And we are now also discussing with other companies. This is we are trying to create an ecosystem of partners or alliances that we could share this technology. And at the same time, we are participating in contributing very actively to standardization so that we can establish as much as possible interoperability among the different suppliers. Obvious benefits of going to IP is this one that I present in this slide. Currently, we have the traditional main routers, which are SDI routers in the broadcast centers, but every time we have to go outside the premises of the network, when we use tie lines to connect the different centers to the main center. Well, and that involves to go electrical to optical, going through optical fiber back to electrical. What about if we could just replace the entire infrastructure using 10 gigabit or 100 gigabit with a complete layer 2, layer 3 type of switching device? It will be really, really cost effective, and we will be sharing all of the different formats and content using that single infrastructure. That's one benefit. Another one that is very important is this is coming from the voice of customers. These are the remote truck operators. To build a truck for high-end production is very expensive. And those operators end up renting the trucks only to special events, the Super Bowl, the World Cup, the Wimbledon games. Therefore, we are missing in the coverage of a lot of sports activity that happen at the local and regional levels because those sports cannot afford the cost of renting these very complex trucks. Then what about if we just could put all of the resources of production in a centralized location and just deliver or move minimum amount of equipment to the venues, to the sporting event venues, and then just bring those signals back to a central location where we will do the heavy production to create the real-time signals. That's something that is receiving a lot of attention in Europe, also here in the US, trying to centralize heavy, complex operations and just relay minimum amount of production equipment to the edges. We have created what we call an IP live production system that is based on software products as well as hardware products that I will talk in detail in a minute. And we are talking to many vendors to try to harmonize, especially the control surfaces. Some of the major customers have already adopted control surfaces from other vendors, and we need to interact with them. Then I'll be discussing the pieces of this IP live production in a few minutes. All right, as I said, why are we talking about IP if we have been doing this for quite some time now in the world of file-based? Well, the remaining challenge that we have is that we have to do this in real time. We cannot use the word best effort. This has to be ultra low minimum latency. And we have to do synchronous processing. The time code that we used to have to genlock equipment will disappear. Everything, we need a new way of synchronizing sources over an IP environment. And also, we need to achieve perfect video switching without any picture disruption. Those three elements have been evading us, manufacturers and the industry at large, for a number of years. But now, recently we have encountered some new tools that permit us to completely answer all of those challenges. One of them is the introduction of something called PTP, Precision Time Protocol, which allows us for sub-microsecond accurate time distribution of information to the network. IEEE 1588 was created in 2008 by the IEEE. And it's a very complex way of sending time information to major production centers or industrial complexes. SMPTE began about 8 years ago to try to produce a SMPTE profile of the PTP protocol. That standard was finally announced at NAB a couple of months ago. Then the SMPTE 2059 is an audio-video signal synchronization standard, and it's made of 2 parts. Part 1 defines a SMPTE epoch, the beginning of time for the IT audio-video environment. And the part 2 is how to relay that PTP information in the form of time packets. Therefore, now we don't have sync waveforms anymore. What we are transmitting is time information to the different elements in the network. Then this picture, you will see we are going to replace the local clock in a broadcast center with so-called PTP master, a precision time protocol master generator. Then the different audio-video sources, the information will be extracted, either uncompressed or compressed. And that data is just data that's going to be packetized in the form of IP packets. What is now relayed among all of the different pieces in the broadcast center is going to be time packets, time stamps. We are going to have masters, PTP masters, and we're going to have PTP slaves. When the data lands on the receiving end, the data is reconstructed and resynchronized based on very accurate knowledge of time information. Okay, now that we can somehow create an IP-based timing distribution technology, let's see what it will take to replace completely an SDI production system. Well, let me point out to you what I think there are 3 planes in the world of a live production system based on SDI. One is the media plane. These are the coaxial cables that join the cameras and the television, the monitors and the switching blocks. Then we have the timing plane. The timing plane is your signal generator, your blackburst. And then we have a control surface or a control plane, which usually controls the SDI router. Well, if we somehow could replace the SDI core, but somehow replicate all of the other functionalities and change the core with an IP router, we may have a chance to move to an IP routing environment. Then let me do that. Then I'm going to change my routing core. I'm going to put an IP fabric. Then the first thing we need to do is convert the audio-video information to IP. Therefore, there has to be an SDI to IP converter. It's a media converter. And then we will use the PTP as part of the timing generator. And the control surface remains the same because you're simply controlling ports. I'm going to switch my camera from this location to this port. That is almost an application layer that can control the IP switch. Therefore, if somehow I could make these 3 planes in the IP world talk to each other, I will have the possibility to create an IP-based, IP live production system. But, all right, here we go. Therefore, this will be my new IP-based audio-video router. But to do this, there are a number of standards issues as well as the definition of special technical requirements. We need to create an LSI, or a media converter, that will take the audio-video signal into IP. We need to redefine the way we look at an audio-video signal, because it's no longer a coaxial cable, it's streams. Is multiple datagrams coming into the switch. Therefore, there's a new definition that we have to establish there. Hopefully, we should obey as much as possible or follow as much as possible existing standards, but as you see later, some of them don't work properly, and we have to modify them. Let's see some of the considerations that the technical requirements that we need to do this audio-video IP-based router. It has to mimic exactly the way an SDI router works. Otherwise, the industry will not adopt it. I need to use the least expensive commercial off-the-shelf Ethernet switches. I need to have sub-microsecond accuracy in order to maintain gen locking of all of the resources over the IP router. That's a very, very stringent requirement. I need to be able somehow to do frame-accurate claim video switching at a very specific time in my video signal without any disruption or tearing of the video. Also, I need to have different essences for different datagrams carrying video, audio, and metadata separately. This is one of the big topics of discussion today that I'll elaborate a little bit more later. And we need to have a mechanism to correct against transmission errors, because UDP is not perfect, and we're going to have transport reliability problems. Then there are a number of technologies already in place, and specifically the IEEE 1588 and the new SMPTE standard, the 2059, for PTP gen locking. I'll go later, I will describe 2022, which is a standard made up of a number of layers. One of the layers is network redundancy. As John pointed out, we need to have redundancy in IP. It's very, very important. And 2022-7 specify how we can do that. It's called hitless failover. All right. Another motivation to move to IP is the transition to 4K. If you decide to stay in HD and you decide to stay in SDI, that's fine. It works. It's economically feasible. We've been doing it for a number of years. But as the industry is moving very rapidly to 4K, and we have built a number of trucks to cover a number of international events in 4K, and 8K will be appearing in the future. Well, we have to use 4 3-gigabit cables per 4K signal. In other words, a 4K signal, 4 to 2, 10 bits at 60 frames per second is going to cost you 12 gigabits per second, 4 3 gigabits. Well, that doesn't work. I mean, the trucks are going to be extremely, extremely expensive and heavy in the wiring. Then it's almost mandatory that if we were to take a 4K to a real practical implementation, that we have to use IP for interconnection. There's no way out. And we are looking at RJ45, we're looking at SFP plus type of connectors, fiber, copper. There is a connector that is now getting a lot of traction in the industry. It's called the SFP plus. Can be used with single-mode fiber and multi-mode fiber. And this is the cable that we are using for long-distance transmission. And there's another cable called the Twinax cable that we use for internal wiring inside the truck. If you decide to use Cat6 cabling, RJ45s, that will only work for about 30 to 40 feet, looking at 10 gigabit interfaces. Okay. We did some calculations. This is the truck, one of the trucks that we built for the World Cup soccer games last year. This truck had 8 4K cameras, about 5 servers, 4K switchers. Well, it was very heavy. It had about 500, almost 600 pounds of cabling alone. We did a calculation that replacing this with a combination of Cat6 and fiber, we could reduce the weight about 85%, which will bring dramatically down the cost of creating these trucks. This is a chip. We call it a network LSI that Sony has developed. And this single device uses, it has 4 3 gigabit ports to accept 4 3 gigabit BNC connectors. It has 2 10 gigabit outputs. It has a network synchronization process. It has forward error correction, SDI to IP mapping, and it has a compressor. It can operate in uncompressed manner as well as in compressed manner. And this device can cover all of the layers that we have in the Internet protocol, including layer 2 and layer 3. The data rates that we are advocating, we are currently using is we can put 4 HD signals over a single gigabit at around 160 megabits per second. We can do 2 1080 60p at around 300 megabits per second. We can do 1 4K signal, 4 to 2, 10 bits, 60p at around 3.5 gigabits per second. All right, we use a compression system called a low latency video codec, LLVC. And this compression system has been submitted to SMPTE. And this is the first time I'm going to talk about it because we wanted to wait until it was submitted officially to SMPTE. It's a very high quality, ultra low latency compression system that uses wavelets. And there are technologies applied to introduce very low latency, and there are technologies applied to increase dramatically the picture quality. It's a line-based wavelet transform. If you are familiar with compression, the other system that uses wavelet out there originally was J2K. But JPEG 2000 is based on a frame-based compression, which introduces very large latency, which is not suitable for professional applications. Then other companies that are also using a wavelet-based compression, they have to use segments of the video. These are number of lines in order to accelerate the compression system. Then we are looking at under a frame, under a fill, a number of lines of latency. Then we design in this chip something called lifting. Lifting is a signal processing technology that is extremely fast, and it works in conjunction with the wavelet filtering to create a very low, this is in the order of lines only, of transition to the coding process. The system is programmable. You can use multiple levels of wavelet compression. We use presently 3 levels of compression. Then this is a graphic picture of, we take this compressed signal and we packetize it in something called transmission units. The transmission units are made up of media payloads. The media payloads are going to be packetized into RTP, real-time protocol, and the RTPs subsequently goes into IP packets. But this has to happen extremely fast. Otherwise, I cannot have a hybrid infrastructure of IP and SDI simultaneously. Then the compressed code stream is divided into media payloads, in other words, packets per line. And then we will do a UDP header, an RTP header. And eventually, that is the essence of the IP packets that's going to go into your environment. At the receiving end, we can start decoding even at the same time that we are transmitting. It's extremely fast decoding process. Then we are talking in the order of much less than a fill of time for compression and decompression. All right, enough of the device. The other element of the system is a network system manager that will look at all of the IP resources that we have in the system. It will operate, it will talk to the IP switch to create the behavior of similar to an SDI router, but you're talking to an IP fabric, switch fabric. Also, it will manage all of the network resources and the capabilities of the different devices in the network. We had to define something new called the AV network node, because now that the audio-video signal is no longer a stream of audio-video in the SDI domain, we have to identify those packets belonging to a single source. Therefore, by identifying those packets, by putting the frame numbers and the source identifications on the headers of each one of the IP packet, we are creating a virtual stream belonging to a given camera or a given production switch. Then by controlling the IP fabric, I can mimic the behavior of punching sources and destinations that we have in an SDI environment. The other capability that's fundamental to the network manager is we have to reserve bandwidth. You can imagine we have a 10 gigabit IP environment or a 100 gigabit environment. There are going to be many components traveling through that highway. They're going to be file-based, they're going to be non-real-time sources. We have to assign priorities. We have to assign bandwidth reservation. The highest priority for control signals, subsequently to each one of the audio-video channels, I have to assign a specific amount of IP capacity so that as they go through the switch, the signal goes clean. Now, John mentioned before, IP fabrics, they switch and they have no idea what they're switching. It could be a PowerPoint, a file base, it's just data packets, and the IP fabric has no idea of the notion of a frame. It doesn't know about whether I'm switching audio or I'm switching video. And the technology for switching in the IT domain is called IGMP, Internet Group Management Protocol. And essentially, you tell the switch to join a stream or leave a stream, or adopt a new packet from another stream and leave the packet or the series of packets from the other stream. When you do that, you may be breaking, you may be switching right in the middle of your frame. Then we have to design a new technology to do clean picture switching inside without creating any new hardware or modification to the existing off-the-shelf IP fabrics. All right, let me describe to you how this chip that we have produces clean video switching. There are probably other ways, but this is a very efficient in terms of silicon manufacturing. All right, the first thing we need to do is, and remember, John mentioned we have source switching, IP fabric switching, or receiving or destination switching. We have adopted destination switching. Then we have the network LSI sitting in my cameras or in my production switcher. And the first thing we need to do is to identify the source and make sure that the frame numbers are embedded in the IP packets. Therefore, these audio-video signals now are identified, and I assign each one of these IP packets with the correct frame number. Then I'm moving from the synchronous zones to the packet zone. Then it is the receiving end, the destination, that's going to command the IP switch to join a new stream and to abandon the old stream. Okay? And we have no idea how fast that IP fabric is going to switch, or how much is the latency of between the ordering of the command and the execution of the command. Therefore, there's going to be an overlap of packets between the two streams. All right? Then the receiving device is now facing two streams that are overlapping. But the synchronization and the correct identification of the switching point is made by the receiving device. And I know exactly where my vertical blanking is, because I know exactly each one of the packets that belong to a frame. And I will switch perfectly, and I will discard the overlapping packets. And I will restore my audio-video signal in synchronous fashion, because I have PTP information as well. Right? Then these devices always output two streams, because we have to have redundancy in the network. Okay? Therefore, it's the PTP information plus the two sources of streams that will connect in the system. Then at the output of the switching action, my switch signal will be exactly 1 frame delay compared to the 2 inputs. That frame delay is to take care of any possible latencies in the actual IP switch, also to take care of the few lines of latency that exist in the compression and decompression. Therefore, well within 1 frame, we maintain perfect synchronization of all of the IP sources in the system. All right, just a summary. The stream senders, the cameras, the production switchers will send the IP streams. The action of switching between streams will be executed by the receiving end. We'll issue the IGMP messages to the switch. I will execute the switch, discard the unnecessary packets. Okay, therefore, I have now made an IP switch fabric behave like an SDI router. The other very important requirement is one of network redundancy. In today's IP environment, when an IP switch fails or a port in a switch fails, there's an indication that the port failed, and then we switch to a redundant network. That's how everybody does it in the IT world. Well, that doesn't work in television, because by the time you switch, you have distorted completely the output. Then what we have is we constantly issue 2 streams into 2 networks. Once we detect, by means of the network management, that one of the ports is oversubscribed, we switch to the redundant network without missing 1 single IP packet. This is called hitless failover, and is defined in SMPTE 2022-7. All right, speaking of a standard, and John did a very good job mentioning this, but we have the SMPTE working on this topic for now over 8 years, with the conclusion of the 2059. We have the video service forums and the joint task force. And there are over 160 chefs cooking this meal. Okay, and everybody wants something there. And the existing standard that we have, that have been created over the years, is SMPTE 2022. And the joint task force is making some recommendations to create a reference architectures and maybe some modifications. Once again, remember, we have the video signals are going to create the bytes that will go into the IP packets, and then we put them into the real-time protocol encapsulation, and then the user datagram encapsulation, then the IP encapsulation, and eventually is the datagram that goes onto your Ethernet or IP cabling. And very important, layer 2, layer 3, transport layer, session layer. All right, these are the 7 standards so far issued by SMPTE 2022 through a number of years. In the beginning, the 2022-1 was a point-to-point transmission, how to send MPEG transport streams, compressed. And we have forward error correction associated with that transmission. And then we had a constant bit rate compress, and we have variable bit rate compress. We had non-piecewise constant variable bit rate compress, a number of variants. And some of them, no one uses them. Some of them are used minimally. And then about 5 years ago, there was a new standard called 2022-6, the high bit rate media signals over IP networks. And associated with that, that was a point-to-point transmission. And this was mapping of a complete SDI or HD-SDI payload over an IP stream. And associated with that, there was another standard, the 2022-5, which was forward error correction to protect that SDI stream. And 2022-7 talks about seamless protection or hitless protection. All right. The issue is that we have is that in production, we need live production. This is not point to point. I have to be able to switch instantly between sources. The forward error correction defined by 2022-5 is not frame aware, doesn't understand the notion of a frame of video. And that forward error correction algorithm can cover information belonging to multiple frames. That's a problem. I'm going to show you in a minute. And the other one is when we map SDI completely onto a single IP stream, every time I want to do an audio insertion or audio modification or metadata addition or anything to the video, I have to demultiplex the whole stream, go back to baseband, and then after I finish whatever thing I'm doing, go back to IP. It's a mess. Therefore, we do not support 2022-6. And a lot of vendors are now realizing about this. All right, we are proposing, we submitted this to SEMTI, a frame-aware boundary protocol, a forward error correction, and also a multi-datagram, video, audio, metadata separately on IP packing. This is the proposal on to replace, or will not replace, it will be a new standard, I don't know, 2022-8, is basically, instead of simply an SDI single stream, and also, by the way, 2022-6 doesn't support compression. Therefore, if I have to transmit 4K, how am I going to put 4K into 10 gigabits? I need compression. The 2022-6 will not support that. Then we need to create a new mechanism, and it's essence-independent mapping over IP, so that I can put video, audio, compress, uncompress. And this is the problem with 2022-5. Currently, it is a possibility that the forward error correction algorithm overlaps information belonging to multiple frames. If you happen to switch at that point, you will destroy the forward error correction algorithm. You cannot reconstruct your video. Therefore, we need to, we are proposing a frame boundary aware forward error correction so that the algorithm ends itself as soon as it sees the end of the frame. Okay? You can read a lot about this in the latest issue of SEMTI. There is a very detailed article by some of my colleagues describing what I just presented in this PowerPoint. The 2059, 2059-1 and -2 is available. It took us 7 years to get an agreement, but it's a very powerful standard. And also soon, it will, the RDD, the registered disclosure document of the low latency video codec, will be available also publicly. All right, some people say, well, why don't you use ABB? Some of you may be aware of audio-video bridging. We will not use audio-video bridging for one reason. The premise that we are looking in transitioning to IP is to use commercial off-the-shelf switches with the least amount of complications and complexities. And to use ABB, you need transparent clock switches or time-aware switches, which are layer 2 switches. ABB will not go through layer 3 IP infrastructure. Then graphically, if you are within a studio or within a building and you have a single LAN infrastructure, ABB could work. You even have bandwidth reservation within ABB. But as soon as you cross from a layer 2 to a layer 3 infrastructure, the ABB datagram doesn't go through. Therefore, this is one of the reasons why ABB has not gained a lot of adoption in the professional environment. All right, let me just move on this. Okay, let me show you some of the initial products that we introduced at this NAB and what's coming in the very, very near future. And we call IP Live Productions. We introduced a new system manager that is what we use to create the integration with other vendors. We need to be able to use control surfaces and routing devices from other vendors, and that will be part of the system manager. And we have a signal processing frame that will accept a number of converter boards that I'll show you in detail in a minute. These are the functions of the system manager. It will create the cross-point switching capability of the IP fabric, emulating what you think is an SDI environment, but we are dealing with IP. It will create, or it will keep track of the well-being, the health of every port in the system. It will know if a port is oversubscribed. It will switch to a redundant port. This is a signal processing chassis that can accept up to 18 cards. These cards, we can put 4 channels of HD over a gigabit, or 1 4K signal over 10 gigabit. Notice in the bottom, there are always 2 ports, because one is the main port and the other one is the redundant port. And you can select whether it's RJ45 or SFP plus connectors. Okay? We also have an audio board, but based on something that John said earlier, we are looking very closely to design a new card based on AES67 and for audio over IP. And there are a number of vendors very popular in the industry, and this is work in progress. All right. Just wanted to show you this. This was one of the big hits at the show, at the NAB show. We introduced a new switcher. This is a production switcher. It's a very fancy console, but this console can be used with today's SDI routing and production switches. But primarily this console, this panel, was designed to operate with a new processor. This processor, we had it working at NAB, is a 4K switcher. Actually, 2 of them make an 8K switcher that we are delivering to NHK in Japan. Therefore, this processor has a number of blades and you can select SDI connectors or RJ45s or SFP connectors. Okay? This board that you see there, you see the 4 big chips. I think I can move, yeah. These are the SFP connectors, main and redundant. This chassis or this card can support 4 4Ks or 16 HDs. And you can order the card either with SFP connectors or with SDI BNC connectors, okay? And this is a large processor. We are going to introduce next year a medium-sized processor. The goal is the following. We want to remove the SCI router and the switching matrix routing portion that exists inside the switcher in order to reduce the cost of the production switcher. And if we could do that, we will only be selling you a panel and a signal processor. And we will be calling the sources from an IP router. Then this is where ultimately we would like to be. This is today's skeleton of a production switcher. You have an SDI router, you have an input matrix, you have the mix effects, and you have your re-entry to do your special effects. Ultimately, sometime in the future, I would like to just use an IP router matrix and maintain a little bit of re-entry matrix to do baseband processing, but we are not there yet. Then this is a hybrid switcher where I will use IP routing as well as SDI routing. And as the end user gets more comfortable with IP, you will be replacing the SDI ports with IP ports, okay? Therefore, there is the situation where you will have to mix inputs from IP and inputs from SDI on the fly. And the operator will not know whether you are operating on IP or SDI, because that conversion has to be ultra fast, very low latency. This is the key advantage of that codec. Anyway, this is a 4K switcher, It has format conversion in every single input so that you can do SD, HD, all the way to 4K. And we can do 160 inputs on HD. We can do 40 inputs in 4K. Okay? And all right. This unit will be commercially available by the end of the year. We are talking, because we cannot make all of the pieces of the system, we're talking to a number of companies. We have very close relation with these companies, and we are exchanging a lot of data. Some companies are thinking about using our technologies. We have a lot of discussions to establish interoperability of IP streams. All right, just to conclude, we think that we are here, that we have achieved a workable, a real-world professional environment of IP production. And we are proposing changes to some of the existing standards, or additions to the existing standard, in order to make them work properly in real-life environment. And we look forward to the changes that the IT industry brings us. And this is one of the key issues, or key objective of moving to an IT and an IP environment. Thank you very much.